surface, and I think that'll be great for everyone.
Great. We have more questions on the phone line, so I'm going to keep going back there, but I do want people in the room to know that if you want to stand up, I will call on you at the microphone if you decide you have a question to ask. For now, please, let's take the next question on the line.
Thank you. Next is from Aylin Woodward from Wall Street Journal. Your line is open.
Hi, thanks so much. Just a couple of clarifications. So once you've locked on to Dimorphos, if you need to make a course correction, are you utilizing the hydrogen propellant, and are you utilizing those onboard thrusters? And then I just wanted to also clarify that basically a round trip communique from the spacecraft to Earth and back would take a little over a minute, given that it's 38 seconds one way, correct?
A right to both. We're using hydrogen thrusters to perform all maneuvers in terminal. We demonstrated our next sea thruster for a couple of hours early on in the mission. That has been completed. Now we're using hydrogen only. So we have 12 hydrogen thrusters. That's what's actually going to be propelling us towards the asteroid. And then for your other question, that's right, 38 seconds. So multiply that by 2, it's over 70 seconds. So over a minute round trip light time. But what you're really looking for is the time that the images are going to come back to Earth. And so there's close to 10 seconds of processing, 5 to 10 seconds of processing on top of the 38 seconds of it, just round trip light time. Sorry, one-way light time. Round trip, one way.
So,
Good.
Just to add, on impact day, at the moment of impact, just so you're not confused, you're going to hear messaging that we've lost radio contact, and there's still going to be images coming through and being displayed once per second for about 8 seconds, and those are images that are traveling through space, and they've hit the ground. We've detected that we've lost radio contact, but those images are still working themselves through the pipeline and being displayed. So when we kind of have some guidance to the team that just so that no one's celebrating too early, that we'll get that message of loss of contact, and we'll still be seeing it. And we're basically, you'll hear Lena will say impact, and she may put other words around it, but
hopefully yes.
But that's where we have very high confidence that we did hit the asteroid, and that we can let the guard down on the Mission Operations Center, and people can relax.
Yeah, and of course you will also see the images of Dimorphos extremely close up. Our last image is probably going to be from about 2.5 seconds prior to impact. So the Draco field of view is actually going to be completely filled with this beautiful image of Dimorphos.
I do need to add one thing to that, since we're talking about that wonderful moment when impact will occur. The engineering team will be celebrating, and the astronomers at that moment will be saying, okay, time to get to work.
That's true. That is very true. This mission has 2 parts. The first part is hitting the asteroid. The next part is actually measuring what happens afterwards, as Tom said earlier.
So for those of you on the phone, the first person who wasn't Lena who spoke was Ed Reynolds, and the second person was Tom Statler, so you know who to attribute information to. With that, we will go to our next question, please.
Next is from Dan Bergano from Grid News. Your line is open.
Hi, thanks for the name identifications. Dan Vergano on Grid News. I'm wondering if the impact happens and Dimorphos is diverted, that 1% factor you talked about, what does that tell you about how much lead time or how much distance from Earth you need to deflect an asteroid about its size, moving about as fast as it is from hitting the Earth? And sort of a code of that question is, in terms of spotting those asteroids, what is the delay of NEO Surveyor now to at least 2 years or mean in terms of being able to spot these kind of things coming in? Thanks very much.
Okay, this is Lindley Johnson and Arctic, those two. As I said, it is very scenario dependent on what the lead time is and would be needed, and depending on the technique. As I said, that any technique that changes the speed of the asteroid in its orbit about the sun is a viable technique. It's just a question about how much you make that change. So a kinetic impactor of DART size, well, DART is specifically sized to have the desired effect on Dimorphos, which is a small moon. If we were faced with an asteroid in orbit about the sun heading towards Earth, it would depend on the size of the asteroid, how much we would need to hit it with. In the case of a kinetic impactor, it would probably need to be larger than DART. And we also might hit it with several kinetic impactors, each having its own, stepping down the speed of the asteroid to affect the change. Other techniques might take longer or shorter, depending on the size. So that is all the kinds of things that need to be assessed once we are dealing with an actual threat. The second question you had was with the budget reduction in the NEO Surveyor project. Currently, we have a budget that is over on the Hill for the appropriations. It will depend on what Congress does with that budget, of course. But that budget will allow us to launch not later than 2028 with NEO Surveyor. That's about a 2-year delay than what we were looking at earlier, but luckily, time is somewhat on our side in this business. A asteroid impact is an extremely rare event. Maybe once a century. Is there any asteroid that we would really worry about and want to deflect? And only maybe once in 1,000 years, an asteroid the size of Dimorphos, on average. But the important thing is to get the capability up and find them. NEO Surveyor will be able to find the population of asteroids 140 meters and larger within about a 10-year period. And that's, a very short period in geologic time. And unless we happen to be particularly unlucky, I'm not worried about an impact in that kind of a time frame. But it's something that we need to get done, and so that we know what's out there and know what's coming, and have adequate time to prepare for it.
All right, moving on to the next question.
Next question from Brett Tingley from space.com. Your line is open.
Hi, thanks for taking my question. I'm wondering, in the course of the development of the SmartNav system and the trajectory correction systems, did you conduct any hardware testing, like flight tests, so to speak, or was it all completely computational? Thanks.
I think I'll take that one. Yes, we have done a lot of different flight tests. Okay, first, of course, we've done a lot of testing on the ground, because you shouldn't fly anything that you haven't tested on the ground. And we did a lot of testing on the ground with computer simulations. But once we launched, we actually have done quite a few tests where we're looking at stars and trying to fool the SmartNav system that two stars right next to each other are Didymos and Dimorphos, and tracking them. We conducted those tests. And then recently, and that's something that we published in the news recently, is that we've been watching the Jovian system, so Jupiter and its moons. And we actually watched Europa exit from behind Jupiter. And we fooled our SmartNav that Jupiter was Didymos and Europa was Dimorphos, and we actually watched the separation happen. And why that is important is because in the last 4 hours during our terminal phase, when the spacecraft is completely autonomous, we're going to watch Dimorphos emerge from behind Didymos. So we already trained the system to do this in flight. So we're looking forward to it. I think we can do it.
Thanks so much. Continuing with the phone lines. Next question, please.
Next question from Jeff Faust from Space News. Your line is open.
Good afternoon. A couple quick questions, probably for Tom Statler. You talked about getting the measurement of the change in Dimorphos' orbit within days or weeks. Do you have a sort of a more specific estimate about how soon you might be able to know what the new orbit is? And then how quickly after the flyby do you expect to get images back from the LiCiCube spacecraft? Thanks.
Yeah, this is Tom. I'll take that. So I'll do this in reverse order. So LiCiCube is being controlled by Ozzy right now. They are testing out their systems, and they will be taking images as fast as they can, storing them on board. The rate at which they're able to download their images depends on their exact state after the flyby. It depends on the availability of the Deep Space Network, and the Deep Space Network helps to communicate with and navigate with everything in deep space. And we have a lot of things in deep space, and we may have more things in deep space soon. But Ozzy will be prioritizing early download of the images that have the best chance of showing us that we have a confirmed impact and the ejecta plume from that impact. But the data rate will be fairly slow, and so I don't think we should be expecting more than a couple of images per day on average coming back from LiCiCube. Now, on the other question, you were asking me to predict when we're going to get the first indication of the orbit change. I think it's fair to say that different parts of the investigation team have their own ideas about that, and they're competing with each other. I think the optical observers and the radar observers have a friendly rivalry to see who's going to get it first. I don't want to get into the middle of that debate, but I think I would be surprised if we had a firm measurement of the period change in less than a few days, and I would be really surprised if it took more than 3 weeks. But what that says is, again, we're doing the test because we want to understand how this asteroid is going to react, and we really don't know until we do the experiment.
Great. We will move on to the next question, please.
Next question from Alexandra Whitsey from Nature Magazine. Your line is open.
Hi, this is for Lindley. I want to follow up on the NEO Surveyor question if I could. How much would NEO Surveyor need to be allocated by Congress in this funding round to make it back onto a 2026 launch?
So we do have basic information about that, Alex. So why don't I follow up with you offline, and I will get you what information we can, okay? Thanks. So though I'll give you an opportunity to ask a different question right now if you want, since I know you've been in the queue.
No, my others have been taken. Thank you.
Great, Alex, I'll follow up with you. Fantastic. Let us go on to the next question then.
Next question from Marcia Smith from spacepolicyonline.com. Your line is open.
Thanks so much. I was wondering if someone could provide a little more detail on what you expect to see from Hubble, JWST, and Lucy. I think someone mentioned that you'd be looking for images or some other spectra of the dust that might come up from the impact, but what exactly are you looking for, and what different wavelengths will each of these be looking at? I guess Hubble looks invisible and JWST in infrared, and what about Lucy? And how far from JWST will DART be?
Tom Statler.
I can take some of that, but that's quite an oral exam you gave me. I'm not going to remember all of those numbers, so I'll have to get that to you after the fact offline. So Hubble will be observing. So Hubble and JWST and Lucy will be observing starting before the impact to some number of hours, a varying number of hours after the impact. And I should back up 1.5 step because, of course, as I said, the most important observations are those that tell us the period change of Dimorphos. But observing what's going on just in the first few hours after the impact, what we're looking for there is an overall brightening of the whole system, indicating how much dust and other debris got kicked up, because that ejecta goes into space and it is also lit up by the sun, just increases the total amount of surface area of stuff that's shining in the sunlight. And just being able to measure how much that brightening happens and when does it happen is a measure of something about the consistency of the material that was lofted up and how much there was. So all of these telescopes are going to be observing over that time. Hubble, I am pretty sure, is observing in the optical region of the spectrum. Hubble is going around the Earth, and so half of the time it's behind the Earth. So Hubble won't actually catch the exact moment of impact. That's okay, because we don't really expect anything to be really observable from the exact moment of impact. But Hubble observations will start about 15 minutes after the impact. JWST, because it has to readjust periodically to pick up new guide stars, may not be observing again at the exact moment of impact, but will pick up just a few minutes afterward. And Lucy will be observing from roughly twice as far away as the Earth is from Dart and Didymos, from a different direction. Lucy will be observing with its LORI imager, which is very similar to Draco, actually, and it's only a 4-inch telescope, and so it will see very faint object brightening. LORI is also an optical imager. JWST, I would have to go and check with my colleagues to find out exactly which instrument, which camera, which wavelengths it's observing at.
And I can follow up with you offline again and see what information we can get to you. But for everybody, if you check out nasa.gov/DART, we are going to be updating as soon as we get imagery and we find out more about it. We'll be putting things up there. And it looks like Lena has a follow-up.
I was going to give a number, which was we're going to be impacting Dimorphos at 7 million miles from Earth. So you can imagine that JWST and Hubble are going to be in that vicinity in terms of the distances.
Yeah, well, JWST is at the L2 point,
L2
which
points,
is a million miles out. So subtract a million miles and 5.8.
Yeah, so here you go. You're welcome.
All right, we will take the next question, please.
Next question is from Alicia Sowers from Mashable. Your line is open.
Hi, thank you. I think this is for Ed. I'm wondering, in terms of Monday, what's your probability calculation for hitting or not hitting the target? I'm just trying to better understand how likely it is that it will hit Dimorphos. And then if you could indulge us, what part of the event leading up to the impact really concerns you the most, and it's sort of like keeping you up at night as we get closer to it?
Let me start the last question first. So what concerns me the most is the weekend. So there are 44 people in the mock, and they're all, each one has a level of criticality, so as we go into the weekend, especially like Friday and Saturday, it's like you just want the team to stay safe, and so we built DART in the middle of a pandemic. We're still in the middle of a pandemic, and so you just want to make sure people are not getting sick or having family in distress with other issues. So the thing that I would like to see, Monday morning is we have a fully populated mock and everyone is healthy and well rested and in the right frame of mind. So with regard to probability of hitting, we've been doing, since we've launched, almost continuously we do mission simulations, and we don't do them in a vacuum. We actually do a lot of measurements in space with the spacecraft. Like we point it to the exact attitude that we're going to be in terminal, and we do things like, let's do a lot of thrusting just because we have big long solar arrays, and let's see how they behave, and and we collect that data. And then we take that data and we fold it back into our models, and we continue to do mission simulations with the new data and refining it. And Lena had talked about parameters. And so a lot of these, we don't do simulations just to do simulations. We do it to learn and to figure out what are the best parameters to have on the spacecraft as we begin. And as we kind of, the Dimorphos and Didymos, Dimorphos begins to reveal itself and how the algorithm behaves to what's revealed, we're going to get maybe some insight as to, hey, that looks like the mission sims that we did like 3 months ago. And so it's kind of a good place to really go and look at, how everything's behaving, and should we adjust a parameter. And so we're, with all of this rehearsal and with all these measurements, we're in a very, very good place to do this Monday's event. That said, Dimorphos is just barely over 100 meters in diameter. It's not very big. We're at 14,000 miles per hour. We're approaching something that we've never seen before. So, to quote the past, we do things because they're hard. We're at the point where technology is emerging so that we can use these emerging technologies to protect ourselves against these threats. And so that's why the T in DART is test. And so it's test and learn. And I think we've prepared ourselves for this moment. But I don't worry about the spacecraft. I don't worry about the algorithm. They're not what keep me up at night. I worry about my team. I worry about my daughters. And so I think we're ready.
Great, thank you so much. We are going to try and get to as many questions as we can, and we'll go to the next one, please.
Next question is from Tim Fernholz from Quartz. Your line is open.
Oh, thank you. Sorry, my question has been asked. Thanks.
So I think we can move on then, but thank you.
We'll move to the next question. Jake Robbins from the We Martians podcast. Your line is open.
Hey there. Thanks for taking the question. I'm just wondering about the AutoNav software. How much of that software was created brand new for DART, and how much of it is legacy software that maybe comes from other missions? I don't know if it's New Horizons or something similar.
I can answer that. So we actually created the software specifically for DART. It does not come from other missions. Smart navigation is based on some of the algorithms that are used in the missile world, just because, they're also interested in hitting small things in space. But this is the first use in space, and we had to change a lot of things to actually make it flyable.
Thanks so much. And on to the next question, please.
The next question is from Kenneth Chang from New York Times. Your line is open.
Thank you. So now I don't think in space successfully with Deep Impact and OHA. So I was wondering, how much harder is this one? Is it a lot harder because you haven't seen Dimorphos yet?
Oh, I'll take this one. Yeah, you're spot on. It is extremely hard for multiple reasons. Deep Impact and other missions, they really are looking at the asteroid. The sizes of those asteroids are much, much larger than what we're going to be hitting with DART. We don't really know what the shape of the asteroid is. We don't see it until the last hour, and that point is just a pixel in the field of view. I mean, at 3 minutes prior to impact, 2 minutes prior to impact, it is 42 pixels in size. That is, and you're moving extremely fast. And at that point, you cannot really send any commands in. So your system has to be very, very precise in how it's controlling the spacecraft, what information we're taking in from all the different sensors on the spacecraft, in addition to the telescope itself. So yeah, it's a little different.
All right, we have 4 more questions we'll be taking. We may go a little past the hour, though we might try to be quick on our answers if we can. Going on to the next question.
The next question is from Asia Farrington from KEB 9 News. Your line is open.
Hi, thank you. So you mentioned that it could take anywhere from days to weeks to figure out if this mission is successful. If it is successful, are there any plans to build more DART spacecraft for future use or for even future tests for larger asteroids?
This is Lindley. I'll take that. For the spacecraft part of the mission, we'll know immediately if it's successful, because it will have hit the asteroid. What Tom was referring to earlier was the observations that have to be taken to determine just how much effect it had on the orbit of the asteroid, which could take days or weeks. As far as if this is a successful, or is we're going to build a fleet of DART spacecraft or something like that, this is just the first test of a technique to divert an asteroid. We want to test other techniques. I mentioned the gravity tractor and some other things earlier. But also, as I mentioned, an asteroid impact, a threatening asteroid, is a quite rare event. We don't know when the next one is going to be, which is why we have to be looking for them to determine that. But our strategy is to find that population out there with a mission like NEO Surveyor and know where all the potential hazards are, and then have sufficient time to then build the right campaign of missions to go out there. One of the first missions we would probably do is what we call a characterization mission, send the spacecraft out for at least a rapid flyby of the asteroid, so we get a really good idea of what it is we're dealing with, so we're not having to do like DART is and not even see its target until almost before it hits it. And then be able to decide what is going to be the best technique to use against this asteroid. No, we won't have a standing fleet of DART spacecraft. Besides, when the next threat comes, technology will probably have moved on, and 30, 40 years from now, who could imagine what technology we might have available to deflect an asteroid.
Great, thank you. We will move on to the next question.
The next question is from Sabrina Ortiz from ZDNet. Your line is open.
Just to clarify, will there be 2 live stream events that the public can watch, and are they happening at the same time? So the Draco images on NASA TV, and will the live video be on nasa.gov.live? And if both of them are happening at the same time, which would you recommend they tune into?
All right, let me clarify. Both are actually on NASA TV. However, one is on the media channel. So the quiet live feed of the Draco camera is starting at 5:30 p.m., I'm sorry, and it will be on our NASA media channel. The broadcast starts at 6 p.m., goes till 8 p.m. Did I get that right? No, 7:30. I'm sorry. Goes to 7:30. And it is also on NASA TV. I just gave the URL, which is nice and simple to find, which is nasa.gov/live. And I can't tell you which one to watch, except we're putting a lot of work into that broadcast, and I know it's going to be great. So that's my suggestion. Then we will have that imagery from the Draco camera as part of that broadcast as well. So you get a twofer by watching the broadcast. All right, we'll go to the next question.
The next question is from John Kelby from The Independent. Your line is open.
Hey, great. Thank you very much. You did hit on some of these elements, but I was hoping we can kind of bring the threads together. I presume that if there were a threatening asteroid right now, you wouldn't feel confident building just a scaled-up DART to do a deflection mission. So what are some of the specific things you'd like to learn from DART that would, leave you with the confidence to make a kinetic impact mission that could actually deflect an asteroid really threatening Earth? And are there any already known limitations on that? For instance, is that not the route you would use to deflect, say, a comet, but you would a smaller asteroid? Thank you.
Let me try to answer real quickly part of that question, and that is about the spacecraft, the spacecraft operations and such. DART, will demonstrate the technology that could be used, the autonomous navigation capability, smart nav, and having a camera like Draco on board. So the sort of the end-to-end system of the spacecraft will give us confidence that such a spacecraft could be built if there were a threatening asteroid discovered. The rest of your question is sort of dependent upon the characterizations of an asteroid. I don't know, Tom, if you want to add anything about that. We do need to learn more about the population of asteroids out there.
Yeah, I can take a little bit of that. I mean, yes, we need to know more about the populations, and so this is where where NEO Surveyor will be tremendously important, not just to find that population, to understand what is the range of different properties. As far as the DART outcome goes, I know that one of the things that I would like to know is the outcome from the DART experiment in line with what we expected on physical grounds, on simulation grounds beforehand? Because if it turns out that our expectations for how a solid object would behave, for example, ends up being very much in line with the way a real asteroid behaves, that means our physics is pretty good and we can use that to predict what we would do in a new situation. On the other hand, if the asteroid responds to the DART impact in a way that's totally unexpected, that might actually send us back to reconsider whether, to what extent kinetic impact is really generally usable. So we certainly hope to learn as much as we can. And being surprised is a good thing, because that's when you learn stuff, when your expectations are not met. So the DART experiment is going to be very exciting. As a scientist, I fully hope to be surprised by the results of the experiment, although as a planetary defender, I don't want to be too surprised.
Yeah, so I'll add just one more thing. There have been a lot of lessons learned for DART and for the operations team of how we would actually operate a mission like this, because the way it was designed was that it had a lot of other technologies demonstrating as well, and we would really design it for the kinetic impact in a way where we have many more guidance and control sensors that would be able to tell us more about the system. We would not have large floppy arrays because we want to keep the spacecraft as lean and as trim as possible. Also, we might want to go faster instead of bringing more mass. So these are all different things that you would have to study depending on what you want to do for real.
All right, thank you. We have two more questions. I'm going to take one more on the phone line, and then we'll take one in the room. So phone line, next question.
Thank you. And the last question is from Sarah Lang from Christian Science Monitor. Your line is open.
Hi, I'd like to ask, and this can be for anyone, you to articulate what feels the most innovative about this approach to NASA scientists. I mean, being the first planetary defense mission that's been conducted. And does it open the door for future opportunities within this field?
Anyone?
I'm kind of the layperson of the group here. So the thing I found the most interesting is just the test itself. So if you just went and hit an asteroid out in space, you'd hit it, you'd change its velocity by 1%. But the problem is with the trajectory and what we know about that asteroid, the uncertainty is so great that you would not be able to measure that 1%. The unique thing about this approach is the moon. You've got a moon asteroid around a bigger asteroid. You can measure the period of the asteroid very precisely, and we're like 11 hours and 55 minutes. And you can get that looking at light curves. And then you hit it, you change its velocity, you change its orbit period by, we think we're going to change it about 10 minutes. Our requirement's about 73 seconds, but we actually think we're going to change it by about 10 minutes. Looking at the light curve, you can measure that very precisely. And so it's just the whole unique aspect of this whole test that to me, it's like just when I first heard about it, and I knew about the error bars on the asteroids and their orbits, and then I heard the whole moon approach. I thought it was brilliant.
Great, thank you so much. Oh, you want to add more? Tom
A little bit more.
Statler?
This is Tom. Let me go after the broader picture of how it's innovative, because we haven't had an opportunity to say that yet. We are moving an asteroid. We are changing the motion of a natural celestial body in space. Humanity has never done that before. And this is stuff of science fiction books and really corny episodes of Star Trek from when I was a kid. And now it's real. And that's kind of astonishing that we are actually doing that, and what that bodes for the future of what we can do, as well as our discussions of what as humanity we should do. It opens up an amazing frontier that is very exciting.
And also just how exciting it is for the public, right? To be able to, here's a mission that you can really get behind and really can understand very easily, and just how fun it is to move an asteroid in space.
All right, we're going to end with one last question in the room. If you'd identify yourself too, please.
Hi, I'm Zach Savitsky from Science Magazine. Tom, just following up on your answer from previous, do you have or can you elaborate on how NeoSurveyor could tell us about the internal structure and composition of potentially hazardous asteroids? And are there any plans for doing that sort of assessment prior to future kinetic impacts?
So NeoSurveyor would give us part of the story, because NeoSurveyor, when it flies, will give us the ability to, first of all, find lots of objects, and secondly, measure their sizes directly, which we haven't had an opportunity to do. And you combine that with regular optical telescope data, then you very quickly get the distribution of reflectivities for all of these objects. So you get immediately a survey of sort of different mineralogical types in a very rough way. Then, if you're ever in a situation where you need to respond to a dangerous object, the most important thing you would need to know would be the mass. Now, if we have by that time also really good information from other missions on how mineralogical types correspond with density, then knowing the density and the volume, the size gives you mass, and maybe that helps you respond in a way that may not be quite so reliant on sending a reconnaissance flyby, for example. But every piece of information is a partial step to where you really want to be, but it's definitely a contributor, even though it wouldn't be the answer to all of our questions.
Thank you so much. I want to say thank you to everybody for joining us today. We are going to wrap up at this point. If there was a question you didn't get answered, please feel free to reach out to our press team here at NASA headquarters, and we will get you an answer. And in the meantime, get ready to watch our show at Monday evening at 6 o'clock on nasa.gov/live. Additionally, as I mentioned, we will continue to have updates about imagery at nasa.gov/DART after that. So both of those URLs are the places to keep informed. And thank you so much. Looking forward to Monday. Thanks.